Mhm. Good morning, ladies and gentlemen. So here from PLN Engineering, in collaboration with Institute Teknologi Bandung, we will present our paper entitled Techno-Economic Analysis of Biomass Cofiring Application on Indonesia 660 megawatt class subcritical coal-fired power plant. So in here, this paper will present by Alfian and Muhammad Royan. Let me show you the fact about the development of carbon tax regulation in Indonesia. On 2023, Ministry of Energy and Mineral Resource released the decree about carbon tax for CFPP on coal-fired power plant. So the main things inside the decree is about the carbon cap and the carbon tax value. The carbon cap consideration consists of two parameters. The first is production capacity and the second location of the power plant to mine. The higher capacity of more stringent the carbon cap regulation. For mine-mouth CFPP, there will be particular value that different with typical application. The carbon tax concept is like when you have the carbon intensity in terms of CO2 in CO2 per megawatt hour higher than the cap, you will be the subject of the carbon tax payer. And then if you have the carbon intensity below the cap, you will be free of the carbon tax. The carbon tax regulation is $2 per ton CO2. For CFPP with carbon intensity more than the carbon cap, they shall find out the way to reduce its emissions, such as biomass cofiring. On the study, the CFPP object is 660 class non-mammoth, namely Suralaya 5 until 7. Suralaya CFPP is located in the west side of Java Island, Indonesia, in Banten province. The object was chosen because it represents the current condition of the CFPP class distribution. Several of that sites facing the problem where they should pay carbon tax because the carbon intensity is more than carbon cap. On this condition, biomass cofiring is current best solution to reduce its carbon intensity. Biomass cofiring is a concept where biomass substitute the coal portion partially to be injected into the boiler and being combusted to produce energy. This study aims to determine the most optimum biomass ratio to be burned by techno-economic analysis. The fact about the biomass cofiring on pros and cons side. Biomass cofiring can reduce carbon emission. So the biomass will be sourced by the biomass plant and to be combusted and produce CO2 and will be absorbed back by the biomass plantation. That's why the concept called as the carbon recycling. For existing CFPP, it could avoid or decrease the obligatory to pay carbon tax. This one is the advantage for using biomass cofiring as the solution. And then the effect biomass cofiring on operational costs. The use of the biomass cofiring will degrade the combustion efficiency that lead the performance degradation. And it will lead the risk of material damage due to the presence of additional chemical like chlorine and alkali in biomass. With the same specification, biomass also costs higher than the coal. So that's why on operational side, biomass cofiring could increase the operational cost due to the factors above. That's why we need to find out the most optimum point where is the biomass ratio should be conducted, and the solution will be conducted in the techno-economic analysis that will be represented by Mr. Royan in the next slide.
Thank you, Pak Alfian. I will continue the presentation. I will explain the methodology and sequence used in this study. First, before we do the modeling of power plant, we need to gather some information, that is biomass characteristic, coal characteristic, power plant characteristic, and financial input data. And then using coal characteristic and power plant characteristic, we can model the existing power plant using thermoflow 31.0. And then the result of the existing power plant modeling, we send the data to the financial calculation alongside with financial input data. And then the existing power plant modeling enter to the off-design modeling, which is add biomass characteristic together with coal characteristic and make them into co-firing. And the technical result of the design modeling will be sent into financial calculation to make a conclusion from this study. Next, please. Okay, the simulation was done using ThermoFlow 31.0 to analyze the operational impact when biomass co-firing is implemented. The most significant impact shown by the simulation is performance degradation and carbon reduction. In this study, we use coal and biomass. The biomass is sawdust. The calorific value of the sawdust is lower than the calorific value of the coal. And the graphic here show the simulation results. This is the effect of biomass co-firing from 0%, 5%, 15% to 30%. At net plant heat rate, the value is slightly increased from 0 to 30%, which means that the efficiency of the power plant is slightly decreased. And then the CO2 emission intensity from 0 to 30% is decreasing because biomass is calculated as carbon neutral. And then the fuel consumption from 0% to 30% is increasing. This is happen due to the low calorific value of the sawdust compared to the coal used in existing power plants. Next, please. This is the techno-economic analysis result. This is the co-firing ratio compared to the levelized cost of electricity. Biomass co-firing impact on LCOE varies with the ratio used. A 5% co-firing ratio can reduce LCOE by 0.36 IDR per kilowatt, but higher ratio tend to increase LCOE. This is because higher biomass river don't further reduce carbon tax liability after a certain point. For Suralaya Unit 5 to 7, reducing carbon emission from 1.03 to 0.911 ton per megawatt requires 7.6% biomass co-firing ratio. Beyond this, no financial benefit are gained. The next table shows the net present value, internal rate of return, payback period, and effect on LCOE. At 5%, the NPV shows positive value with the IRR 16.08% per year, and then the payback period is 4 years, and it reduced the LCOE around negative 0.36 IDR per kilowatt. The other, at 50% co-firing and 30% co-firing, the NPV shows the negative value. So the IRR is cannot be valued, and then the payback period is no, because the NPV is negative. And the impact on LCOE, the 15% biomass will increase the LCOE 4.15 IDR per kilowatt, and at 30% will increase 15.24 IDR per kilowatt. Next. Conclusion. Implementing a higher biomass co-firing ratio does not always lead to favorable financial outcome. The decision to implement it should comprehensively consider the relevant regulation. Recently, there have been several Indonesian and PLN regulation addressing carbon tax and biomass co-firing application. If there are updates or new regulation in the future, the calculation should be adjusted accordingly. In this study, the best option for Suralaya Unit 5 to 7 is to conduct biomass co-firing at around 5% ratio. A higher co-firing ratio, particularly above 7.6%, could potentially lead to financial losses for the power plant. In order to increase the use of biomass, it should be considered to reduce the carbon cap value. I think that's all for me and Mr. Alfian. Thank you very much and good morning.